Hello, this is Dr. Hanaa Assil, and this is about ion polarization and electron density maps. So let's take a look at what all of this means. We know that bonds could either be ionic, in which a metal loses electrons, becomes positively charged, a non-metal gains electrons, becomes negatively charged, and they are just standing next to each other, positive ion and negative ion. Or two atoms could share a pair of electrons, and that would be a normal covalent bond. Now, we can indicate these compounds by drawing lines to show that if it is ionic, the electrons of one atom are separate from the electrons of the other atom. So the positively charged cation has its electrons in these shells, so these are drawn as contour lines. The negative ion has its electrons, and that is drawn to show that they are separate if it's ionic, or the outer shell is overlapping, the contour lines of the outer shell is overlapping to indicate that they are sharing. This kind of diagram is called electron density maps. So electron density is the measure of probability of an electron being present at a specific location. So these contour lines or these circles indicate the presence of the electrons. If it's ionic, the electrons of the negative ion are just alone from the positive cation. If they are covalent, they're sharing the outer electrons, so the outer shell overlaps. And that means we can draw something to indicate whether it is covalent or ionic. If we say it is ionic, what we call contour lines, or the shells or the circles to show where electrons are, for an ionic bond they are separate. For a covalent bond they are overlapping. So these are called electron density maps. But then sometimes the electrons are not exactly around the negative ion. Sometimes the presence of the positive cation distorts the electron cloud, so the electrons are pulled a little bit towards the positive ion. Now that is called ion polarization. So ion polarization is the distortion of the electron cloud of the negative ion, of the anion, due to the ability of the cation to attract electrons. So that positive ion is attracting the electron cloud towards it. So we say that the cation has polarizing ability, and the anion is being polarized. And that means if I draw an electron density map, for example, for lithium iodide, I will find that the lithium is a positive ion. That's okay, no problem. The iodide is an ion that has several shells around it, but they are not exactly circular. They are pulled towards the positive ion to indicate that there is what we call ion polarization. So that means if I'm drawing an electron density map for covalent, they overlap. Ionic, they are separate, no overlapping of the contour lines. But sometimes the electron cloud around the negative is slightly attracted towards the positive ion. That indicates that this molecule has a partial covalent character. It is not exactly ionic, in which each of the ions is independent of the other. The electron cloud around the negative is slightly pulled towards or distorted towards the positive ion. Now, when does this happen? when do we have ion polarization? Remember, if the positive and negative ions are almost the same size, the same charge, they are purely ionic. Sodium chloride, for example, would be purely ionic. But if the cation is small and the anion is big, in that case, the electron cloud around the negative ion is attracted or distorted so that it is polarized towards the positive ion. So one of the important cases in which we have ion polarization is if the cation is small and the anion is large. So a small cation and a large anion would be or would have ion polarization. Another case is the charges on the positive ion. So smaller ions with larger positive charge have more polarizing ability. So Na plus, Mg2 plus, aluminium 3 plus, the aluminium is small with high charge, it will have more polarizing ability, and that means the anion would be more polarized, and that means the aluminium chloride has more covalent character. Again, the anion. We said the anion should be large. So if we're comparing aluminium fluoride to aluminium bromide, which one would have more polarization? The anion that is bigger, or the anion that has more charge. So an anion with 1 negative or 2 negatives or 3 negatives, the more the charge on the anion, the more it is likely to be polarized. So what causes polarization? Cation has to be small with high charge. The anion has to be big with high charge. So if we're doing this question, which of the following results in the most polarizing cation? We said if we're looking at the cation, when does it have more polarizing ability? If it is small with a large charge. So we said aluminium 3 plus would cause more polarization than Na plus. Which of the following compounds has the most polarized anion? So if we have all of them have oxide ion, but we have sodium, magnesium, potassium, calcium, which of these is the cation with more polarizing ability? Well, we said it should be small with higher charge. So remember that comparing potassium, calcium, sodium, magnesium are smaller. Now, which one would be more polarizing? The one that has +2. So magnesium has +2. That would have more polarizing ability than Na plus. The bonding in lithium iodide has some covalent character. Remember we said if I'm drawing the electron density map for lithium iodide, lithium is small, iodide is a big anion. So actually the electron cloud around the iodide is slightly distorted towards the cation. Why? Out of these choices, because the lithium ion polarizes the iodide ion. We said when this happens, we say that the bond is not purely ionic. If it were purely ionic, then each electron, the electron cloud would be separate away from the positive ion. But if it is slightly drawn towards the positive ion, then we say it has some covalent character due to the polarizing ability of the positive ion. Again, we have sodium iodide, and we know that iodide is a big anion, so it is likely to be polarized. So if we're asked to draw the electron density map for the iodide ion in sodium iodide, we will draw it something like this, in which the circles or the contour lines are not perfect circles, they are drawn towards the positive ion. Which of these gives the best evidence that the bonding in copper 2 chloride is ionic? So if we have copper 2 chloride and I want to show that it is purely ionic, well, from the contour lines, from the electron density map. We said if it is ionic, then none of the lines would overlap. So there are no contour lines around more than one nucleus. The contour lines are separate around the nucleus of each atom. That would indicate that it is purely ionic. Again, if we're required to draw the electron density map for a chlorine molecule, of course, chlorine molecule means two chlorine atoms having covalent bonds. So to draw the electron density map, we have overlap of the contour line for the outer energy level to indicate the sharing. So remember again, to draw for covalent, the contour lines overlap. Ionic, each ion is independent of the other, no overlap of the contour lines. If there is ion polarization, that means the positive ion distorted the electron cloud of the negative ion, then the electron cloud around the negative is slightly pulled or distorted towards the positive ion. This question says which diagram best represents the electron densities in lithium iodide. Again, if you look at the periodic table, lithium is in group 1 and the iodide ion is large. Therefore, there will be ion polarization, so the electron cloud around the negative ion would be slightly distorted towards the positive ion. Remember, it is the negative that is distorted, not the positive. So this would be the representation for the electron density maps. Which of the diagrams below best represents the shapes of the electron contours in sodium fluoride? Now let's think about sodium fluoride. Sodium and fluorine are small ions with positive, or one positive and one negative. They are purely ionic. So which of these indicates purely ionic? Remember, if they are almost the same size with small charge, so Na plus F minus, the F is not a big ion like iodide, so it is less likely to be polarized, so that would be the electron density map. So just how an electron density map of ammonium chloride would provide evidence for the presence of ions in the compound. Now we said if I have ionic ammonium chloride, the bonds between them are ionic. So from the electron density map, what should we see? We should see that the contour lines go around the ions, do not overlap. And that's the end of this lesson. I hope this was useful to you, and thank you for listening.